Hello. So in this video, what we're going to go through is different ways of measuring concentration of solutions. So we were covering solutions, and the idea was that's a setup where in many instances we're going to have a solid dissolved in a liquid, although you can have plenty of other setups too, like you can have gases dissolved in gases, like the air you're breathing. You can have solid-solid solutions where you've got a solid dissolved inside of another, like metal alloys. You can have gas dissolved inside a liquid, like a soda that you have. If you've got a Coke or something like that, there's CO2 dissolved inside the water there, and sugar and all that other stuff too. So when we do this though, so far we've only talked about it qualitatively. We in chemistry many times want to have a quantitative measurement of exactly how concentrated something is. Also, depending on context, we will sometimes want different units of measurement. So in your first semester of chemistry, you've covered molarity. We'll do that one first, but there are a bunch of other ways we can do it as well. And in following videos, we'll talk some about why you might want to use a different concentration unit, because it's not just because, well, Dr. Leslie wants to give me a test and he wants to make me try to solve problems in different ways. That's not the reason. There are different contexts where we're going to want to use different units of measurement. So let's start with the review one first. So molarity. So for a solution, if you're talking about its molarity, that's going to be related to the moles of solute over the liters of solution. The first thing to highlight here is a reminder, because in 1211 it was always true, but in 1212 this will change a little bit. You'll notice the denominator is specifically liters of solution, not liters of solvent. So this is about how big the total solution we make ends up being. I mention that because some of these later units will end up being specific to the solvent instead of the solution. So you do have to pay attention to that. So we're going to try this problem. So if a solution contains 20 grams, and so I'm purposely doing one that's going to have some extra work. So since you've seen this in 1211, I want this to be a good refresher on a few things from 1211. So if a solution contains 20 grams of calcium chloride dissolved in enough water, and so you'll see the wording that sometimes sounds a little strange, dissolved in enough water to make 500 milliliters of solution. What's the molarity of the solution? What is the molarity? So the wording that you'll see sometimes is that we're dissolved in enough water to make 500 milliliters of solution, instead of saying we just added 500 milliliters of water. Depending on context, sometimes you'll make solutions that there isn't that much solute in them, so the solution changes very little compared to the solvent, so we'll just word it as 500 milliliters of solvent was added. And if you have no other context for it, you can reasonably assume, okay, I'm just going to use that for my volume of my solution. But that's not always true. So we do have to pay attention to that. And in terms of lab, for example, a way that comes up is like, for example, liquid-liquid solutions. When they mix together, their volumes aren't going to be just the two added together because they actually change in volume some. So if I mix some alcohol into some water, like if I take 20 milliliters of alcohol, dissolve it in 50 milliliters of water, I do not get a 70 milliliter solution necessarily. I might get like 68 milliliters. So we do have to pay attention to that at times. But for pure problem solving, if you don't have any other information and they just tell you it's 500 milliliters of solvent, it's okay to assume, okay, that probably didn't change a lot, and it's usually because there just isn't much solute. It'll be like it'll be like 5/100ths of a mole or something, where it's like, practically speaking, chemists know, okay, that doesn't change the volume significantly. So just to keep that in mind. Now, how do I solve this problem? Not worried about this context. So first we identify it asks for molarity directly. That tells us what unit we need to use, so that's why we're going to pick this concentration unit. The next thing we need to see is what's the solute. So we're told the solute is calcium chloride, and we have 20 grams. We're also told that water is our solvent because we're dissolving the calcium chloride in the water, and we have 500 milliliters of solution at the end. So for solution, that's the easier unit to convert. We just have to go from milliliters to liters. Remember to divide by 1,000 for that. So our denominator, we already know that our liters is going to be 0.5000 liters of solution. We've got to do some work on the solute. The solute is 20 grams of calcium chloride. So we have 20 grams, and step one is knowing the chemical formula. So calcium chloride, this is an ionic compound. It's type 1. It doesn't have a Roman numeral. Calcium, if we look at our periodic table, is going to be +2. Chlorine's going to be -1. To balance those charges, for our ionic compound, that means we're going to have 2 chlorides for every 1 calcium. So we have 20 grams of CaCl2. So this is a way to also review ionic compounds when you see a wording like that. Now, on my own test, we will occasionally do that because I do care that you keep up stuff from previous chapters, but I also know it takes time. So many problems I will have written there CaCl2. But we will occasionally intentionally be like, okay, look, we do want you to remember this because over time we want you to get really comfortable with knowing, oh, calcium chloride, that's CaCl2. So now, we got our 20 grams. So if we get our molar mass, if we check our periodic table, we're going to get that this has a molar mass of 110.97 grams of calcium chloride is 1 mole of calcium chloride. So if we do the math there and the grams cancel and we're just left with moles, we get 0.180 moles of calcium chloride. To finish, for our molarity, we just need to plug in moles over liters, moles of solute over liters of solution. So we have 0.180 moles, and we have 0.5000 liters. When we do the math for that, we're going to get 0.360 molar. Remember, we use the capital M, stands for moles over liters. I'm going to go do a reminder up here at the top. So M can be rewritten as moles per liter. And when we're, oh, my face is in the way. There we go. I mean, you could see it, but still. Also, as a reminder, when we talk about molarity, we are talking at some particular solute in your solution. So this is 0.360 molar calcium chloride. So many times we won't put that label in the end because the context of the problem tells you that it's assumed a person being asked this question. If you were in a lab and someone wanted you to make this solution, said, hey, how concentrated is it? I would say 0.360 molar. Now, if it were a solution that contained multiple components, this would be the molarity of just the calcium chloride, and I would need to specify it because it might have some second component in it that also has a concentration that's relevant. So that's our first unit to go back over. That's molarity. Now, let's do another one. So next, we have our first new unit. It's called molality. In textbooks, you'll see an italics M as its unit. I can't write an italics M, so I just have a regular M. And I point that out because, yes, mass is M, molality is M. So context-based, you should be able to figure out which is which, but do keep track of that. Make sure you're paying attention. It's easy when you're doing something really quick to see an M and be like, oh, that's mass. I'm used to that, and then not realize, oh, this is molality based on context. So what is molality? Molality looks similar, but is not quite the same as molarity. It's moles of solute over kilograms of solvent. There didn't need to be a period there. I was just like I was writing a sentence. So this looks similar, but not the same. So a reasonable question I think to ask is, so why in the world do we do it this way sometimes? Well, there's a few things. First, and probably the biggest reason you'll practically use molality sometimes, is that when you're talking at the volume of a solution, that is something that is temperature dependent. So water, for example, has a different density at 20 degrees Celsius compared to 80 degrees Celsius, even though it's a liquid in both cases. That means technically the molarity changes. And you would need to measure that. You need to know the new volume. Now, practically, we do a lot of labs where we don't change our temperature significantly, or even the temperature changes don't change our density enough for us to worry about it. So we still use molarity a lot, but that is a limitation of it, is that technically there may be some changes there that many times in a lab we might not be keeping track of because we're like, well, it's good enough. It gets the idea. But that's not a constant. On the other hand, kilograms of solvent, that's the same no matter the temperature, because mass, unlike volume, isn't going to change with temperature. So that could be a helpful thing. Also, in a future video, we're going to talk about something called colligative properties. So solutions have specific properties, and some of them are related to the molality specifically. So we will use molality in those cases as well, as it makes it easier to calculate those properties. So that's the second reason we'll end up using it sometimes. So you definitely will see, practically speaking, you will usually see molarity in a lab space, but not always. Molality will be relevant sometimes. So you will see both of these depending on the situation. Now, let's take a look at an example with this. So here, we're going to do something similar to the last one. So we're going to say, if a solution contains, we'll go with 25 grams this time, of potassium chloride, and I'm just going to go ahead and write KCl this time. We did the practice already. Dissolve in 500 grams of water. What is the molality? You'll also notice sometimes this one ends up being easier to calculate depending on the units you're already starting with. So we have to start with our solvent is the easier one. So this is 500 grams. That's also going to be equal to 0.5000 kilograms. Hey, looks a lot like our liters from last time. Then we have our 25 grams of KCl. Now let me check what the molar mass of that is. I already did this one. Okay, it has a molar mass of 74.55 grams is 1 mole, which means that we have 0.335 moles of KCl. So to find the molality, our M, we're going to do 0.335 moles per 0.500 kilograms. And from there, we're going to get 0.670 molal of our KCl. So that's how concentrated our solution is. And again, I keep blocking. You could see it, but yeah. Now, what else might change a little bit in your problems to pay attention to? Sometimes you will still be given volume of the solution. You might have been told 500 milliliters. If so, you have to use the density to convert between volume and mass. Now with water, in a lot of contexts, we'll be using 1 gram per milliliter, and then it doesn't change the numbers at all. But that's not always going to be the case. Most solvents are going to have a density other than 1, so the grams and milliliters will not be equal. In addition, if we're trying to be really careful with a particular question, water's density is temperature dependent and will not be exactly 1 gram per milliliter depending on the temperature. It's mostly down to how many significant figures we're working with. Once we start getting to 3 or 4 sig figs, even at 25 degrees Celsius, there's a slight bit of change there. So if we need incredible accuracy, we'll be using something slightly different than 1 in many cases. So that gets us our molality. Now, yeah, I'll go ahead in this video and do the third one. I'd rather make the next one a separate video. Okay, we're going to stop with this video there, and then we've got 2 more units of measurements that we will do in the next video.